And that should be a familiar topic, right, from 21A. And this is more like the chain rule generalized, basically. Generalized to apply to functions of however many variables you want. So let's say I have a function of x of y, which is x squared times e to the 3y, but I happen to know that x really is cosine of t and y is really sine of t. Where might that happen? Remember when we did the parametric curves in chapter 13, the circle, and how the circle is parameterized with a vector function as, remember we had cosine t, sine t, or you could flip it around. Either way, that parameterizes a circle. And so there will be times, especially in 21D, when we want to parameterize some function around a circle. And so we would use this parameterization for x and y. Okay. And then we want to know df dt. What's the rate of change of f with respect to t? So the obvious way, I think, to solve this question is, if x is cosine of t and y is sine of t, why don't we just plug it in? Let's just make this a straight up function of t with x being cosine. So I have cosine t squared times e to the 3 sine t, and then just take a straight up 21A style derivative. However, you do see I would need a product rule, right? Because I've got a function of t there, a function of t there. So I'm going to need f prime g plus f g prime. All right, so the derivative. So we are using the chain rule, but but not in the way that we're really going to be focusing on in this section. Obviously, we are using the chain rule, though. So stuff squared, 2 stuff to the first times the derivative of the inside, which is negative sine t. There's f prime, times g, e to the 3 sine t, plus f, which is just cosine squared t. I'll write it the same way. Times the derivative of e to the 3 sine t, which is e to the 3 sine t, times its derivative, which is 3 cosine t. Not too bad. But another way we could, I kind of think of this as twofold for a reason here. Number one, to explain the chain rule again, what we're doing. And number two, I could certainly dream up another problem here where writing this out as a function of t and taking the derivative would be really, really horrendous, okay? So another way to get this answer using the chain rule, let me actually show you something here. Let me show you something. If you, I got room right here. If you go back to 21A, I'll use this space right here. And remember, like if I had, what's a classic chain rule problem? Let's say I had like y equals x squared plus 1 to the 5th power. One of the ways to explain the chain rule in 21A was we did like a substitution. Like if you let u equal x squared plus 1, then you can rewrite this function. You can think of this as y equals u to the 5th. And you may remember this formula. If I want to find the derivative of y with respect to x, I first have to find the derivative of y with respect to u, and then multiply that by the derivative of u with respect to x. How many people remember that kind of a formula from 21A for the chain rule? Right. In other words, this would be the derivative of y with respect to u would be 5u to the 4th. The derivative of u with respect to x would be 2x. Now that's obviously not exactly the derivative, but all I'd have to do to get the final answer is just replace my u back in. If I just put x squared plus 1 back in, that is the derivative. Okay. Now I wouldn't have done this in 21A because we didn't really need to. It wasn't any worse than this. But one way I could model this is I could say, this is the idea of a mapping. I could say by replacing y with this, I've now written y as a function of u, but I know that u is a function of x. And one way you could describe this chain rule is you could say, if I want to take the derivative of y with respect to x, if I want to go from here to here, I have to first go through this path. This is dy du, that's this one, and then multiply that by du dx. So dy du times du dx. That's how I find dy dx. Okay. Yeah, again, there's no real reason to show that in 21a because it was only one variable. It would always look like that. And so it gets kind of monotonous. But here's what we could do for this problem. Let me make sure I'm showing my problem. Oh, no, I got to back that out here. There we go. So let's try this with a mapping. The way my function's written right now, f is a function of x and y. But I know that both x and y are functions of a different variable t. So my mapping would look like this. I need to slide that up. And kind of in the same spirit as our normal chain rule for 21a is, if I want to find the derivative of f with respect to t, if I want to find the derivative of this variable with respect to this one, I have to go through my pathways. And because I have multiple pathways, right, I have to do this one and this one. Here's what it looks like. From here to here, that's going to be my partial derivative with respect to x, partial derivative of f with respect to x. And then from here to here, that is my derivative of x with respect to t. That's exactly like the chain rule from 21a. But the difference is there's another pathway here. And every time we have another way to get from f to t, we're going to separate that out with a plus, because this is a new pathway. So this would be the partial of f with respect to y from here to here, and then multiply that by dy dt. The way I like to think of it in my head is why we add is that there's two things that affect f, the derivative of f with respect to t. This obviously has some impact on the derivative of f with respect to t, and so does this. So we should combine those, right? We should add them together. Okay, so here's how this would look. Let me rewrite my functions. My function was x squared e to the 3y. X was cosine t, y was sine t. So the partial of f with respect to x, taking the derivative of this, holding y constant, will be 2x e to the 3y. dx dt, the derivative of x with respect to t, is negative sine t. The partial derivative of f with respect to y, x is constant, which is multiplied by my variable, so that just stays there. And the derivative of e to the 3y is e to the 3y times 3. And then dy dt is cosine t. And then the idea is, if you compare, perfect. If you compare what we have right here with the way we did it the first way and this way, hopefully you can see they're the same answer, right? 2x, there's my e to the 3y, there's my negative sine t. Here's my x squared e to the 3y right there, times 3. And then there's my cosine t. I don't know why the 3, oh no, that's right, because it was, yeah, and there's my cosine t right there. So everybody see, they are identical. Now, if I wanted it to be strictly in terms of t, what would I do next is I could substitute x equals cosine t, y equals sine t, right? But oftentimes it's okay to just leave it like this in this section, because we have basically the form of the answer, right? Form of the answer, which is up here. And I'll just put if we want, we can resub x equals cosine t, y equals sine t, and get that same answer. Okay. So this is showing us how to use the chain rule when you've got multiple variables. And sure, I think I'm going to switch order. Let's do this. Yeah, let's do this next. Let's switch orders. I have a context problem here, an actual applied problem here in a second, but I want to stick with this idea of the chain rule and the idea of the mapping. The mapping is really helpful, at least for me. Now I've got a function z, which is the inverse tan of x plus 2y, but I'm told that x really is represented by u squared times v, and y is u times ln of v. Obviously, I could put those in like I did the first time, but that just looks crazy, right? If I put those in there and then try to take the derivative of z with respect to u, that is just going to be too much for me. All right, so we're going to try this, the chain rule, the mapping way. So let's look at our mapping. I'll show you how things can get changed here. So I start with the fact that z, the way it's written, is a function of x and y again. But this time, x is a function of u and v, so I'd have an arrow going from there to there, and so is y. So that would go from here to here. Okay, and so taking my partial with respect to partial of z with respect to u, again, I can see there are two pathways, right? There's this one, and then there's this one. And this kind of helps me make sure I'm getting those. So this would equal, right here, this would be my partial of z with respect to x times my partial of x with respect to u. And then I want to add in, because there's another thing contributing to that derivative, the partial of z with respect to y times the partial of y with respect to u. And see, there's no limit to this, right? I don't know if I want to go there, but I could have made x equals u squared v times e to the w. I could have three. You could have as many variables here, and the mapping is going to help you sort out the correct way to take the derivative. Partial of z with respect to x is going to be remember your derivative of arctan is 1 over 1 plus whatever's inside squared times the partial derivative of the inside, but it's just x, which is just going to be 1. Let's separate that out. The partial of x with respect to u, so I would be treating v as a constant. V's times my variable, so it's just going to come down for the ride. That's just going to be 2u times v. Partial of z with respect to y is 1 over 1 plus x plus 2y squared times 2 this time. Times the partial of y with respect to u. That would be u, that would just be 1. It's going to be just times ln of v. Okay. So let's just do, you know what, I think you get the idea for this one. Let me throw in another example here. Let's say this is 3.5. Let's say my function is x squared y e to the z, but I told you that x is really let's say u sine of v, y is u squared plus cosine of w, and z is u squared w cubed plus e to the v. I don't know, I'm just making up stuff here. Okay, and let's say, just for the sake of argument, that I wanted the partial derivative of my function with respect to v first. Do you see why my point of this is, do you see why the mapping is really useful, right? Is that, whoa, this is kind of overwhelming, but I have seen problems like this. So try to sketch out the mapping and see what you need. So you should have something like this, like f is a function of 3 variables now, x, y, and z. I know there's 3 other variables, v, u, v, and w. X is only a function of u and v, however. Y is a function of u and w, and z is a function of all 3. Crazy. But I can see that there's only 2 pathways that take me to v. So I can follow this. Partial of f with respect to x times the partial of x with respect to v, plus the partial of f with respect to, what's the other one? Z, times the partial of z with respect to v. Let's not worry about cranking out the numbers. I think it's more, what I'm really emphasizing here is how you would set it up. So what if I asked for the partial of f with respect to u? Now, unfortunately, I have to go down all 3 paths. So it'd be the partial of f with respect to x times the partial of x with respect to u, plus the partial of f with respect to y times the partial of y with respect to u, and then with respect to z. And you'd have all those derivatives to work out. So that's what I mean. We're talking about like the generalized chain rule, meaning if you generalize, no matter how many functions you have, intermediate variables like x and y, and final variables like u, w, and v, you can still formulate what your derivative ought to look like. I think we're going to use partial derivatives applied going forward here, but I think the book's a little light on like, okay, we got partial derivatives chain rule. What is this all used for? So this problem stuck out for me from this section. It's you should hopefully, if you've taken some chemistry, you might recognize this formula. Remember the ideal gas law? PV equals nRT. And if we only have 1 mole, N is 1, and I think R is 8.31. I have no clue what the units are. But what is that, like the universal gas constant or something like that? Anyhow. So let's say we've got an ideal gas that's the pressure, volume, and temperature are all related by this equation, as many of you know. Let's say that the temperature is currently 300 degrees Kelvin, but it's increasing at a rate of 0.1 degree Kelvin per second. And the volume is 100 liters and increasing at a rate of 0.2 liters per second. We want to find how fast the pressure is changing. And this should sound familiar. How many people see this is really a related rate question, isn't it? This is related rates from 21A, things changing over time. Let's see intuitively, what do we have an idea of what the answer should be, whether it should be positive or negative? If the temperature increases, what does that do to the pressure? Right? If the temperature of a gas goes up, that usually would imply the pressure goes up as well, right? You're heating things up. That usually would imply that. There we go. But what's happening is the volume is increasing as well. And that would give more space, right, for the gas. So that usually causes a decrease in pressure. So the temperature increase is causing the pressure to get higher, but the volume increasing is causing the pressure to go lower. In that sense, I have no really, it's really going to matter with the numbers of whether the pressure is actually going to be increasing or decreasing. It's all going to depend on the numbers themselves and the relative rates of change of each of those. Okay. Well, the first thing I would do is, if I want to find how fast the pressure is changing, is I'm going to solve this equation for P. P is going to be 8.31 T over V, or 8.31 T V to the negative 1. And here's how we could view this. The way we've solved for P is a function of both the temperature and the volume of our gas, which in this situation, we know are both functions of time. So if I want to find how fast the pressure is changing, dP dt, I've got a map that will tell me how to get there, which is I'm going to take the partial derivative of the pressure with respect to temperature, multiply that by the change in temperature over time. A common question, I don't know if anybody's thinking this, but I'm reminded because I did this in 17C earlier this quarter. And how do you know when to use a partial versus a straight up derivative? Partial is when whatever you're taking the derivative has more than one variable, right? But my temperature is strictly a function of time, right? I don't need a partial symbol here. It's only a function of time. That's why I'm using dt dt versus partial. Same thing over here. I want my partial derivative of my pressure with respect to volume, but my volume is strictly a function of time. So multiply that by dV dt. All right, let's see what we get. We'd get the partial. Yeah, and as our first example said, right, a lot of times with partial derivatives, especially, I really don't want to use the quotient rule unless I absolutely have to. So the same strategy I did on my first problem, right? If I'm going to take the partial of P with respect to T and treat V as a constant, then I'm going to just bring this up. And I don't even need a product rule, right? If V is constant, that's a constant. The derivative of this with respect to T is just going to be, my constants come down, 8.31 V to the negative 1, and the derivative of T is just 1. dt is given in the problem. That's how fast the temperature is changing over time. So that would get multiplied by 0.1. Partial derivative of my pressure with respect to T, with respect to V, that's respect to V. So I'm treating T as a constant. All of this is constant. So I'm just going to do the power rule. It's going to be negative 8.31 T V to the negative 2. And dp dt is the 0.2. And then you would just plug these numbers in. 8.31 times 0.1 is 0.831 divided by V, which was given to be 100 liters. And then I don't know what that is. 0.1, if I multiply 0.2 times 83.1, that would be negative 1.6. Wait, 0.8 is 1.662, is that right? And yeah, times my temperature, which was 300 degrees Kelvin, and then divided, I'm going to bring this back down, by volume squared, 100 squared. I have no clue what that is. I need a calculator. Or maybe I do. You guys are probably faster than I am. I did this one earlier and did I get an answer? I got a slightly negative answer, negative 0.00, nope, negative 0.04. .155 kilopascals per second. Yeah, that would have been my unit of time. Okay, I'm going to go straight to this problem. All right, chain rule. Here's another neat thing about the chain rule is it can be used. Remember implicit differentiation from 21A? If you don't worry. We're going to review it really quickly here. Back in 21A, you were doing implicit differentiation when you had a function like this where your y's were buried in with your x's, right, into your equation. In other words, it wasn't solved to be y equals some function all of x. And in some cases, that's impossible to do. If I tried to solve this for y, I don't think I could do it because you've got a y squared there and e to the y. And what implicit differentiation was all about is that if we assumed y is some function of x, in other words, we're supposed to, when we see y squared, we're supposed to assume that there's some function of x being squared. And same thing up here, e to some function of x. Then what we found is if we just took the derivative of both sides of this equation with respect to x, the derivative of x cubed with respect to x is 3x squared. And then remember, this was that thing with implicit we had to get used to. If you encountered a y term, knowing that it really stood for this, the derivative of some function of x squared was 2 times that function of x to the first, but that function's just y. And then we had to tag on the derivative of the inside, dy dx, right? Because that's what you would need according to the chain rule. In other words, when you encountered a y term, you just took the derivative the normal way and then tagged on a dy dx. But if we're assuming y is a function of x right here, and then x times e to some function of x, that requires a product rule. So we would need an f prime g plus f g prime. Derivative of e to the y would be e to the y, and then we have to multiply by the derivative of y with respect to x. And the derivative of the right side, the derivative of a constant, would just be 0. And then what we did was we shuffled some terms around. Like let's leave this term and this term on the left side because we want to factor out the dy dx. And we take the terms that don't have dy dx, we move them over to the other side. Because for these two terms, we could factor out dy dx. And then just divide. Now, I'm going to factor out the negative from the top. That was a quick review. Hopefully you still remember how to do that. But it turns out with the chain rule, we can actually make this process easier. And this one wasn't terrible. I mean, what made it a little bit worse was we had this product rule. But the one I'm going to do next in a second, do you see x cubed y to the fourth? If I was treating y as a function of x, there's a product rule. There's a product rule. This next problem I'm going to do would require two product rules, and that's just going to get ugly. So it turns out there's a nice way to do this now that we know the chain rule and we know how to take derivatives of functions of more than one variable. The idea is this. We're going to take that same equation we had up here, and we're going to think of this as some big function f, capital F of xy. Basically, if I move the 7 over and set all of that equal to 0, this is the same as that, right? Because the solution to this, if I move the 7 over, is exactly what we were taking the derivative of. Okay, and then the idea is this. We would want to then take the derivative of both sides with respect to x. Now, take derivative of both sides with respect to x. But now the way I'm going to view this is this, okay? This function right here, f of xy, is a function of both x and y. But remember, the whole key when we do implicit differentiation, what we're assuming is that y really represents a function of x when we do this. So my mapping would look like this. F is a function of x, clearly, right? It's got x in it. It is also a function of y, but we know y is also a function of x, or at least that's how we're seeing it, right? That's how we're assuming when we do implicit differentiation. So this is my mapping. Almost looks like one of those recycle things, huh? But this is what I mean. We're going to take the derivative of both sides with respect to x. Well, the derivative of 0 with respect to x is going to be 0, right? We know that this is going to be 0. So my right side is going to be 0. But to take the derivative of the left side with respect to x, I have to follow my pathways by the chain rule. This right here is, let me just use the subscript notation. That is capital F sub x. That's the partial derivative of f with respect to x. But there's another pathway, which we know gets separated with a plus. This right here is f sub y, takes me from here to here. And from here to here, what is that? That's the derivative of y with respect to x. And if I solve for dy dx, since that's what we're interested in, you would first subtract the f of x, so that's going to be negative f sub x, and then you would divide by f sub y. So check this out. Let's apply it. We already did the derivative, but let's make sure we get the same answer. Look at how easy this can be. Now, if someone wants dy dx for this crazy equation, what I first do in the numerator is, what is my partial derivative of this function with respect to x? In other words, I'm treating now y as a constant. If y is a constant, then the derivative of this would be 3x squared. This is a constant all by itself. It goes away. The derivative of x e to the y with respect to x would just be e to the y, because that's constant. That would just come down, and this would be 1, over my partial derivative of this function with respect to y. Now x cubed would go away, so it'd be 2y plus x stays there, and the derivative of e to the y is e to the y. Which is exactly what we got when we did it the old 21a way. Exactly what we got. So kind of a nifty tool. If only we had known that back in 21a, well, though we wouldn't have known what partial derivatives were. I guess there's no way to go back and make that any easier. So let's try that. Try that on this one. And I'll just get you started with this one, is that in order for this to work, this formula, what you want to do is set your function. Think of some bigger function where you move everybody to one side. So you'd want to have x cubed y to the 4th. Let's add this over here. Subtract the 1 and set that equal to 0. So it's just negative f sub x over f sub y. We can compute this really easily. If y is constant, this is going to be 3x squared y to the 4th. Derivative of this one with respect to x would be cosine y. Partial derivative of the bottom of this with respect to y is x cubed times 4y cubed. X stays there. It's going to be plus x times negative sine of y. Done. Super easy, right? Way better than doing 2 product rules and all that stuff. Yeah. Now, this is a nice shortcut for a 21a problem, right? When we just had two variables here, right? X and Y, 2 variable calculus. But we can, this same shortcut, you know, we've been dealing with a lot of functions like when I wrote, like when we do it, let's say a parabola, right? F of x, y equals x squared plus y squared, a paraboloid, right? All of these things we've been dealing with so far have been functions where z is explicitly written in terms of x and y, right? So here's basically the equivalent to what we just did, but for a three-dimensional surface. So here, z is implicitly a function of both x and y. Remember when we did it for 21a, we had to say y is implicitly a function just of x, but now we have z is implicitly a function of both of those two variables. And so let's say I have this equation and I want to find the partial of z with respect to x, which would imply y is being treated as a constant. You can actually just take your normal derivative. For example, the derivative of x with respect to x, this would be 2x. If y is a constant, that would be 0. This would be 2z times the partial of z with respect to x. But because x is a function of x and z is a function of x, you would need a product rule right here. It wouldn't be that bad, actually. But this whole idea of the chain rule bailing us out of tricky implicit differentiation, you can extend this idea. So the same idea what we just did, let's let f be a function of x and z, because remember, we're treating y to be constant. And just in the same spirit as the last one, we're going to move everybody over, set this equal to 0. And we're going to take the partial derivative of both sides with respect to x. Oh, I kind of already did it. I don't know why I filled that in. Because what I wanted you to see here was that, yes, f is a function of x. It's also a function of z, but we're treating z as a function of x as well. Okay, and right now we're pretending y is a constant. So this would be my mapping. And if you do the same thing and the derivative of the right side is going to be 0, you're going to get f sub x plus f sub z times the partial of z with respect to x equaling 0. And so my partial of z with respect to x, if I solve for it, it's going to be negative f sub x over f sub z. Oh, I see that. So I could get this derivative by just doing negative the partial of this whole thing with respect to x. With respect to x. And when I do this partial with respect to x, I'm treating y and z as a constant here, right? So that's going to be 2x. That's constant. That's constant. Minus 3yz. X and z are constant. Because I don't think we did partial derivatives with multiple variables here. So if I'm doing f sub z, then I'm treating x and y as a constant. So my f sub z would just be 2z minus 3xy. And perhaps you're picking up on something here. Where did it go? Back here, if we wanted dy dx, it ended up being negative f sub x over f sub y. Notice it was the reciprocal. If we wanted the partial of z with respect to x, it was negative x f sub x over f sub z. What do you think this one's going to be? Partial of z with respect to y. It's going to be negative f sub y over f sub z. See how it's kind of the reciprocal, right? That's one thing I've always noticed that makes it easier to remember. And so you would just get, for f sub y, I'd be treating x and z as a constant, so it'd be negative 2y minus x and z are constants, so minus 3xz over f sub z would be 2z minus 3xy. We just did that right there. Yeah. I don't really feel like I have enough time to start the next section, which is, I never did figure that out. Let me see. Maybe we'll just wait till next week. I don't think we're in a super big hurry right now. It's directional derivatives. Yeah, that's a really big topic. Show the mapping for B. Yeah. So if I wanted this is good practice for me. So if I want the partial of z with respect to y, that means I'm treating x as a constant just for this derivative. So my mapping would look like this. What I would do is the same thing. I have the f right here, but I would say f is now a function of y because that's my variable of interest. It's also a function of z, but I'm assuming z is a function of y. And so if I had my like f of yz, that's why I put yz because I'm treating x as a constant. So I'm pretending that's a constant. So if I took the derivative of both sides, you would have f sub y from here to here plus f sub z times, this would be the partial of z with respect to y, which is what I want, and that would equal 0. And that's how I get this formula.